Hello and welcome to this brief video, which is going to be the conclusion of our lecture on the multiplication rule and independence. So I wanted to start off by reviewing this example here. In this example, we had two events, getting a red ball on the first draw and getting a red ball on the second draw when you're drawing from a vessel that has two red balls and two blue balls. And the question we were asking, the question that was posed, are A and B independent? The answer depends on whether or not you replace the first ball after you draw it, right? So we went through case one, and we said the thing we need to check is if the probability of A and B is the same as the probability of A times the probability of B. Now, probability of A, probability of getting a red ball on the first draw, which is just going to be 2 out of 4, okay? Probability of B, getting a red ball on the second draw. Again, you're replacing whatever ball you drew on the first draw. So for probability of B, it's still 2 out of 4. Okay, so the right-hand side is going to be 1/2 times 1/2, which is 1/4. And for the left-hand side, we said, what's the probability of A and B? And A and B is you get a red ball on the first draw and you get a red ball on the second draw. And to calculate that, what we did was we said, let's look at the outcome space overall. You can get two reds, red and a blue and then a red, or two blues. So the only way to get a red on the first and a red on the second is this first out of the 4 possible outcomes. Totally works, totally fine. So we get 1/4 on the right, 1/4 on the left. So our conclusion was yes, the events are independent when you replace after the first draw. Then we moved on to case 2, which was asking about what happens when you don't replace. And here we went through two kind of computations. So the first one was, how do we compute the probability of getting a red ball on the first draw? We said that's still going to be just 2 out of 4. The second expression here was the probability of getting a red ball on the second draw. I said that's actually going to be a combination of the probability that you get a red ball on the first draw and then a red ball on the second draw, plus the probability that you get a blue ball on the first draw and a red ball on the second draw. So we multiplied those two together, and it ended up that the probability was exactly the same. So it's still 1/2. The probability that your second draw is a red ball is still 1/2. Seems like it should be different, but it was the same. And then here's where I started to doubt myself. I said, okay, well, what about the probability that you get a red ball on the first and the second draw when you're dealing without replacement? And here's where I said, hey, I need to double check and verify, is it the case that it's really going to be 1/6? Remember how I got this was, I said 2/4 is the probability that you draw red. And now, because we're not replacing, when you remove that red one, you now have a 1 out of 3 probability to draw a red on the second. Yeah? And this is, in fact, true. And let's prove it. So let's actually give a proof. And the proof that we give can actually go back to the formula that we had in the beginning of the slides. This is going to be the same as the probability of B given A times the probability of A. So this is our multiplication rule. Now, what is the probability that you get a red ball on the second draw, given the fact that you got a red ball on the first draw? Well, if you got a red ball on the first draw and we're not replacing, then the probability of getting a red ball on the second draw is 1/3. So that's why we have the 1/3. And now what is the probability of getting red on the first ball, on the first draw? Well, that's going to be 2/4. So when we multiply this together, we will indeed get 1/6. And we'll say, oh, the probability of A and B is 1/6. The probability of A times the probability of B is 1/4. So not independent. Okay, and this matches kind of what we would expect, because if you are not replacing, then what happens on the first draw is going to influence or impact what happens on the second draw. So it makes sense. Okay. And then after that, we looked at an example where we had many events, and we're talking about events being independent. We're picking tickets, right? Pulling tickets out. Why we care about independence with many events is because oftentimes when we're doing statistics, our methods are relying on the assumption, or our methods depend on the assumption, the hypothesis that your processes are independent. In real life, that's probably not going to be the case. But if the population is large enough, it doesn't matter, because the percentages end up being so close to each other. Okay. So that was the point of the next example, that example there. And the last problem we want to do, we'll do this one. This is a birthday problem. This is kind of a famous example. So we want to make sure we kind of cover it. The question is, what's the minimum number of people needed to be in a room so that the probability that at least 2 of them have the same birthday is greater than 50%? And it feels like, hey, there are 365 days in a year, so maybe you need to have something like 365/2 in order to guarantee that, or, in order to have a probability that at least 2 people are going to have the same birthday. That's really not how this ends up working out. So let's actually use probability and the principles we've been studying so far to determine the minimum number needed. So here's kind of how I want to approach this. We're going to let n equal the number of people in the room and our goal is to figure out the smallest value of n so that the probability that at least 2 of the n people have the same birthday. So our goal is to minimize n satisfying probability that at least 2 of n people in room have same B-day. So we have a function that depends on n, right? You change n, you get a different probability. I want to find the first value of n, the smallest value of n, where this probability is greater than 50%. So let's just, to get an idea of this function, let's see what do we get if n equals 2. So if n equals 2, what is the probability that at least 2 of the people in the room have the same birthday? So we've got our little room here. This is our room. You've got 2 people. And the question is, what's the probability that at least 2 of them, in other words, what's the probability that they both have the same birthday? Well, that probability is going to be, well, we need the total number of ways they can have birthdays over, or that'll be our denominator, is the total number of ways they can have birthdays, which is going to be 365 possibilities for the first person, because this person can have 365 different birthdays, right? 365 choices. And now the second person can also have 365. Now, how many different ways can they have the same birthday? Well, the first person, 365 ways, but once we know the first person's birthday, then the second person needs to have the same birthday. So our numerator is actually going to be 365 times 1. Okay, so let's go over this again. Denominator, this is going to be the total number of ways two people can have birthdays. So like maybe, 1 1 and 1 1, 1 1 and 1 2, 1 1 and 1 3, 1 1 and 1 4, right? All the way down to December 31st, December 31st. So 365 options for the first one, 365 options for the second one. Total number is going to be the product of the two. The numerator is now going to be, another way to think about it is to say, how many different ways can they both have the same birthday? Well, they can both have January 1st. They can both have January 2nd. They can both have January 3rd. So there are 365 ways they can both have the same birthday. Okay, so all in all, what is this probability? So this is going to be, the 365s cancel out, 1 over 365, which is approximately, I'll use my calculator here. Okay, so that's about 0.27%. We're looking for the smallest value of n where the probability is 50% or more. Okay, so n equals 2 is too small. Okay, what happens if n equals 3? What's the probability? Now notice our question here is at least 2 of the 3 people have the same birthday. So you have 3. You have 3 people in your room. And, so let's add a third person. We want to know the probability that at least 2 of the 3 people have the same birthday. So maybe these two have the same birthday. Maybe these two have the same birthday. Maybe these two have the same birthday. The easier computation is to say that this will be 1 minus the probability that it's not the case that at least 3 people have the same birthday. Or at least 2. So we want the complement of that. So now, how do we figure out what the complement of that is? Okay, we'll think. So for our possible outcome space, they could all have same B-day. So all 3 of them have the same birthday. Or 2 of them have the same birthday and 1 of them don't. Or they all have different birthdays. So these are all the possibilities. And if we're trying to figure out at least 2 have the same birthday, that means exactly 2 have the same birthday or all 3 have the same birthday. So the complement to at least 2 of the 3 have the same birthday, the complement would be they all have different birthdays. Okay, so I'm going to write this is the same as 1 minus the probability that they all have different birthdays. And now I've got to figure out how to compute the probability that they all have different birthdays. Well, how many birthdays are possible? 365 options for the first person, 365 options for this one, 365 options for that one. So it'll be 365 cubed for the total possible birthdays, or the number of ways that the 3 can have birthdays. Now, how many different ways can they all have different birthdays? Well, 365 options for the first person. The second person now has 364 options because whatever is the birthday of this one, the second one can't have that same one because we're trying to count the number of ways that they have different birthdays. And then the last one, 363, because they can't have whatever birthday this person had or the birthday that the first person had. Okay? So when I compute this with my calculator, I'm trying to see if we get something that is at least 50%. So I have 365 times 364 times 363, and I need all of that divided by 365 cubed. Okay, and then I need 1 minus that. Oh, that's going to be 0.008. It's like 0.008 something, so that's about 0.8%. So with 3 people, it's more likely that at least 2 of them will have the same birthday than if there are only 2 people in the room. But we're nowhere near 50%. And in general, let's see if we can come up with a formula for the probability given a random n, or just an n, okay? So let's add here. And I'm going to try to modify what we've done here and see if we can use this framework to generalize to the case where we just have n. Okay, so maybe what if n is equal to just, I don't know, k? And now we want to know what's the probability that at least 2 of the k people have the same birthday. What's the complement of at least 2 have the same birthday? So let's see here. If I have k people in the room, I don't know how big k is, so I'm just putting, people in there. But k is whatever it is. They could all have the same birthday, which means all k of them have the same birthday. Maybe k minus 1 of them have the same birthday. K minus 2 have the same, k minus 3 have the same, right? Exactly, k minus 4 have the same. So I can organize the cases or organize the possibilities by the number of people that have the same birthday, right? And I'll have exactly 0 have same B-Day. So none of them have the same birthday. Everybody has a different birthday. 2 of them have the same birthday. 3 have the same birthday. And all the way up to, they all have the same birthday. So even in this instance, I'm looking for the complement of at least 2. So at least 2 means 2 have the same birthday, 3 have the same birthday, 4, blah, blah, all the way up to 10 to k. The complement to that is they all have different birthdays. So I'm still going to be computing 1 minus the probability that they all have different birthdays. Now, how do I figure out the fraction that represents this? Well, if I have k people in the room, how many different ways can I have birthdays? 365 to the k. And now, how many different ways, or how many ways can they have different birthdays? Well, the first person is going to have 365 options, and then 364 options, and then 363 options, 362, all the way down to 365 minus k minus 1. So think back, how did we get k minus 1? Think back to when we had 3, we went 365, 364, 363. We need to multiply 3 numbers, and each time we're subtracting 1 from the previous, right? So this 363 is 365 minus 3 minus 1. Here, when n was equal to 2, we had 365 minus 2 minus 1. That's how we got this one here with the 364. So it'll be 365 minus k minus 1. That's the last term that we're multiplying. So let's put it all together here and see. And the denominator will have 365 to the k, and in the numerator it'll be 365 times 364 times 363, 362, and you keep going all the way till you get to 366 minus k. Because if I have 365 minus k minus 1, that's the same as 365 minus k plus 1. That's the same as 366 minus k. So this is my probability, and I need to find the smallest value of k. Such that this is bigger than or equal to 50%. And so we can put this into a spreadsheet, I guess, or you can put it into, whatever way you like to kind of calculate this, right? You do a little chart, k, and then this probability, right? So k equals 2, we got something like 0.27%. For k equals 3, we got 0.8%. And you can just run the numbers, and I think it ends up being something like k needs to be at least 26, I think. Let me see if I wrote it down. Answer ends up being about 23. So k equals 23 is the first time your number ends up being above 50%. Okay, so important things with this problem. First of all, how do we set it up, right? So understand it as an optimization problem. Second of all, how do we compute or figure out the formula for the probability based on n? And it turned out that the way to do that was not to add up a bunch of different scenarios with our addition rule, but to instead look at the probability of the complement. Yes? And then the third thing is, let's take a step back and look at the assumptions that we made when we were determining this probability. So one of the things we were assuming, our assumptions, and maybe we can write them in, write them in purple. We started off here, and we did the same thing here. We assumed that each person entering the room had 365 days that could be their birthday. That means we were not allowing the possibility that somebody was born on February 29th. Right? So we were assuming no one is born on leap year. Oh, on leap day. The second thing we were assuming, when these people, right, so if we have two people, the second thing we assumed is that this person's birthday is independent of this person's birthday. If we had the added information that this person is a twin or a triplet of this person, all bets are off, right? Probability that they have the same birthday is going to be 100%. We we're assuming in our calculations that the birthdays of the people are independent. So the people aren't related, it's, we're not at a convention of people with birthdays on January 1st, right? The people in the room are not related to each other and their birthdays are not related, their birthdays are independent. So this is why we were able to kind of say, whatever is the birthday of the first person, when the second person walks into the room, right, the second person is now going to enter the room, what's the probability that their birthday is the same as the first one? Was 1 out of 365, right? So whatever is, we have one person in the room, they have their birthday, is determined. Now a second person walks into the room, whatever their birthday is, they've got a 1 in 365 chance that it's the same as this person's, right? And now over here, right, two people, this person, probability that they have the same birthday, or this person walks in the room and that the new person's birthday is the same as this one or the same as that one. Instead of adding up those probabilities, it's easier to do the complement, right? But regardless, we're assuming that the birthdays are independent and that no one is born on February 29th. Okay, so it's okay for us to basically use the product rule, or use the multiplication rule, where we're just doing the products as opposed to doing conditional probabilities. Okay, all right. So as usual, if you have any questions, please let me know, and I'll see you all next week.